Hi, my name is Shahnawaz. In this lecture, we will discuss pullbacks and morphisms. But first, recall that if, say, x in an and y in am be affine algebraic sets, then a polynomial map from x to y is a map given by polynomials. That is a map, say, if f1 to fm be polynomials, then a polynomial map from x to y is a map from x to y given by these polynomials. Here these fi's, they are in the polynomial ring k x1 up to xn. uh, so this map takes the point p in x to the point, to the m tuple f1p up to fmp. So this implies that whenever we are given an m tuple of polynomials in the polynomial ring, then the tuple determines a map from x to y. A bijective polynomial map whose inverse is also a polynomial map is called an isomorphism. So this is what we have studied in the previous lectures. Now, given a polynomial map, say this map, so then the map, so if I restrict each polynomial to x, then this map defines the same polynomial map. Now if x is in an is a closed subvariety, so a polynomial function f from x to k on x is a restriction, is the restriction of polynomial to x. That means a polynomial function is a function such that f of p is f of p for all p in x. So this is the polynomial function. Now we know what the polynomial maps are and what the polynomial functions are. Also, the polynomial function on x is a, if we consider the set of all polynomial functions on x, that set forms a ring under pointwise addition and multiplication and is isomorphic to the ring ax, which is a coordinate ring of ax. Mod ix, where I is the ideal of x. So this is isomorphic to the set, to the ring of all polynomial functions on x. So ring of all polynomial functions on x. So therefore we can also write a polynomial map. So if we are given a polynomial map, say f restricted to x1 up to fm restricted to x from the set x to y, so we can write this polynomial map as the m tuple f1 up to fm, where these fi's are polynomial functions. These fi's are the restrictions of fi to x. So that means these fi's, they are the elements of the coordinate ring. Now let us define the pullback. So we have the definition here. So let us consider x in an and y in am. So let us suppose they are the affine algebraic sets. So be affine algebraic sets. So Or let us suppose they are the they are the varieties. Let us suppose they are the varieties. We don't mention whether they are the projective or affine varieties. So let x and y be varieties. Uh, let phi from x to y be a polynomial map. That means this phi is determined by uh, an m tuple of polynomials to be a polynomial map. Then the pullback, then the pullback of a regular function, I mean of a regular function, say h uh, in ay, so is phi star h, where phi star h is given by the map h composed with phi. So this is the definition of pullback. Now we claim that this pullback is actually a polynomial function. So let us prove this. We have a proposition. The pullback, I mean, let us write this way. So if phi from x to y is a polynomial map between varieties x in an and y inside an, then the pullback, then the pullback of, I mean, then the pullback of h inside ay is a polynomial function as well, is a polynomial function, that is phi star h is an element in ay. Sorry, ax. So let us prove this. So since h is an element of ay, so since h is inside ay and this ay is isomorphic to the ring of polynomial functions on y, so this is isomorphic to the ring of polynomial functions on y. So we can write this h as, so we can write this h as the restriction of some polynomial h to the y, where this h is some polynomial in the polynomial ring, uh, say y1 up to yn. So now this right being and this phi being a polynomial map, we can write this p as an m tuple of polynomials. So write phi equal f1 up to fm where uh, so where these fi's, they are the polynomials in the polynomial ring k x1 up to xn. Then for any points, let us consider a point in x. Then for any point, say a1 up to an in x, we can write p star of h of this point a1 up to an. So we can write this as h of phi of a1 up to an. But this phi is given by this polynomial map, so this is same as, I mean, this is h of f1 up to fm of this point a1 up to a n. So this is same as, now this is same as h of f1 of this point a1 up to an, so on up to fm of a1 up to an. Now this is same as the polynomial h in f1 x1 up to xn. Now this point a1 up to n being a point of x, I mean, since a1 up to an is a point in x, so we can write this as f1 up h of f1 of x1 up to xn, so on fm of x1 up to xn. So this is a polynomial. So now we can restrict this to x. So clearly this is an element inside ax. So that means this pullback is also a polynomial function. Now we have some remarks to make. So let us write the first remark. So the pullback, so the pullback phi star, which is a map from ay to ax, which takes an element h in ay to h star, sorry, phi star h. So this is a ring homomorphism. So this is trivial because if you take two elements here, say h and g, then phi star of h and g will be phi star of h plus phi star of g, and same is the case with the product. So one has to verify this. Now we have one more remark to make. So if this phi, so if the polynomial map phi from x to y is an isomorphism, which means that phi is bijective and its inverse is also a polynomial map, then the inducible pullback, I mean the phi star from a y to ax is an isomorphism of k algebras. So one should remember these ax and ay, they are the uh, algebras. Now we have, I mean, we want to define morphisms. So we have the definition. So let us consider x and y to be varieties. So let us suppose they are varieties. So we call a map. So a map phi from x to y. Uh, so this map is a map is called a morphism, or sometimes we call this a regular map. If first item is that if this phi is continuous, and the second item is that for all open subsets, for all open subsets, v of y and all regular functions f which are regular on v, the pullback of f, the pullback of f is actually which is same as f composite phi is a regular function on phi inverse v. Now, why we write phi inverse v here? Why we impose the continuity here? So one should remember that this thing over here makes sense since we always define regular functions only on open sets. So, and as we have required phi to be continuous, so phi inverse v will be continuous. So this condition, the condition that phi inverse phi is continuous uh, um, was put precisely so that phi inverse phi is continuous. So let us write this down here. So the condition that phi is continuous uh, is in the definition so that phi inverse phi is open. So if this is open, then we can uh, talk of regular functions on this set because we always define regular functions on open sets. So thus, for any subset V of Y, we have a K-algebra homomorphism. So thus, for any open subset V of Y, we have a K-algebra homomorphism from the homomorphism phi star from the ring of regular functions on V to the ring of regular functions on the inverse image of V. We have one more definition here. So, we call a morphism an isomorphism if it is bijective, and if it is inverse is morphism as well. So we have this definition. So let phi from x to y be a morphism of varieties, then this phi is called an isomorphism of varieties if phi is bijective as well as phi inverse is also a morphism. Let us make a remark here. So the identity map say id on x, which is a map from x to x. So this is I mean this is a morphism, and so this is a morphism. And if we look at the pullback and the pullback id x star is actually the identity map on the ring of regular functions on U for all open subsets U in X. Also, if we have two morphisms, say phi from X to Y and psi from Y to Z, uh, are morphisms of varieties, then the composition psi composite B, which is a map from X to Z, is also a morphism. And the pullback psi composite phi star is same as phi star composite psi star. Now, to check whether a map between varieties is a morphism is not easy. It is a little bit clumsy, because to check a map as a morphism, first we have to check whether it is continuous, and then we need to verify whether, I mean, uh, if we look at regular functions on open status, whether their pullbacks are also regular or not. So, for this reason, we need some more description of these morphisms. Some criteria which tells us whether a map is a morphism or not. So, for this, we have this result, a proposition which gives a little more description of these morphisms. So, let us suppose phi is a morphism between varieties between varieties, and let us suppose u sub I is an open curve of x, and let be an open cover of X such that if I restrict this P, uh, so this is not a morphism, it is just a map, be a map between varieties. And let these UIs cover X such that if I restrict phi to each UI, which is a map from UI to Y, so if these maps, these restriction maps are all morphisms, so such that phi restricted to UI is a morphism for all I, then phi is a morphism as well. And so this is the first item. And for the second item, so let us suppose x1, which is a subset of X, and y1, which is inside Y, be varieties. And let phi from X to Y be a morphism. So here we are given that phi is a morphism from X to Y with phi of x1 contained inside y1. Then we claim that the restricted map phi to x1 from x1 to y1 is a morphism. Let us prove the first item. Now we are given that, for the first item, we are given that these UIs cover X. So since this collection of UIs is an open cover of X, therefore, if we look at any, open subset W of Y, then if we look at the inverse image of W, that is, that is the union of the inverse image of W intersection with UI, because these UIs they cover X. But this is same as if I look at the union. So this is same as if I look at the restriction map of these UIs, their inverse image of W. Now, since each restriction map is continuous, so these phi inverse restricted to UI of W is an open set. So since the restriction map UI from UI to W, so we are given that they are morphisms, so hence they are continuous. Since this is a morphism for all I, so this would imply that the inverse image under this restriction map of W is open for all I, because each phi restricted to UI is open. So hence this would imply phi inverse W is open, since the union of all these UI is X. So hence phi inverse W is open, since union of these UIs is the set X. So this proves the first item. Uh, to prove phi is a morphism. Now, to prove the second item of the definition of morphism, let us consider a regular function on W. So since P restricted to Ui from Ui to W is a morphism for all I, one can note that if I look at the composite map of, this map, the pullback. So this is a regular function on the set P inverse W intersection Ui. So this is true for all I. So now if I look at the union of all these sets, so we'll get that. So this is same as first, right? So this is same as mm, I mean the this is here, this is equal to the, so it is like this, which is same as the set of all regular functions on Ui on the set phi inverse W intersection Ui. And this would imply that, so this would imply that uh, phi star h uh, is phi star h restricted to the set Ui intersection phi inverse W is an element of, is regular function over the set phi inverse W intersection Ui. So this is true for all I. Now this is true for all I, since these open sets they cover they cover the inverse image of W. So since the collection phi inverse W intersection Ui is an open cover of phi inverse W, one can note that this phi star h is actually regular on the set phi inverse W. So this proves first item. Now to prove second item, uh, first note that so we had to prove phi restricted to x1, which is a map from x1 to y1, is a morphism. So for that we had to prove first this map is a continuous map. So note that phi restricted to x1 is continuous, because a restriction of a continuous map is continuous. So phi is given to be a morphism, so it is restriction to x1 is continuous as well. So this is continuous as a restriction of the continuous map phi from x to y, because phi from x to y is given and to be a morphism. So now let V be an open subset of y1. So let h be a regular function on v. So we have to prove, its pullback is a regular function on some open set of x1. Now, to prove that, remember that being a regular function is a local property. So instead of proving this for v, we can prove this for any neighborhood of an arbitrary point in v. So therefore, we can replace v by a smaller open subset. So the reason is that being a regular function is a local property. So replacing replacing if necessary uh, v by a smaller open subset. So so that we can assume, note that we can always write a regular function as a quotient of two polynomials while the denominator is a non-vanishing polynomial. So we can uh, assume h to be the quotient of polynomials say f and g, while f and g are polynomials, and these polynomials are homogeneous of same degree in case we are dealing with the quasi projective varieties. So they are homogeneous polynomials of same degree in case of quasi projective varieties. In case of quasi projective varieties, and this g is a non-vanishing polynomial on v. So this quotient also defines a regular function. So this quotient this quotient also defines a regular function. Say, let us call this h on an open subset. Say u tilde. Let us call this v tilde inside y, such that v contains v tilde. So in some sense, we are extending this notion of regularity. So then the pullback of this regular function h is a regular function on phi inverse v tilde, as the given function phi is regular, and this phi star h which is same as phi star h restricted on the inverse image of v intersection x1, so is this is regular on this set, I mean the set phi inverse v intersection x1. So this follows from I mean this definition that phi is given to be regular. So now to rephrase this statement, this implies that is this phi star, this little h restricted to x1, which is same as phi star this big H restricted to the restriction map of, I mean the inverse image of the restriction map of phi to x1 of v, which belongs to the regular functions on x1 to on the set phi inverse, I mean the restriction map of x1 inverse image of the map phi restricted to x1 of the set v. So this proves that the map phi from x1 to y1, which is a restriction map x1, so this map is a morphism.